Okay, so hi, we're the student committee for particle discovery, or SCUD, and this is our particle accelerator and detector proposal for finding unparticles.
Oh, push page down. Or down arrow.
Okay, all right. So, to understand unparticles, first, something that needs to be understood is scale invariance. And with scale invariance, normally features of particle scale, for instance, E equals mc squared shows this, relating energy and mass. And however, with something like E squared equals p squared, energy is essentially a non-factor. But with scale invariance, the mass of an object, could vary along with other variables such as energy, and therefore becomes undefined with scale invariance in terms of mass, meaning that it becomes undefined and therefore can be, it essentially becomes that mass becomes undefined, and therefore it's stuff that is named unparticles because it acts like particles, but it's scale invariance.
Okay, so the motivation for particle searches are purely curiosity-based, so this wouldn't really solve any existing physics problems. But it's just to explore something that is peculiar. So as Ye-Jun previously stated, particles are scale invariant, but also they are non-trivial scale invariant, meaning that they have mass. So the energy squared is given by mass squared plus momentum squared, and multiplying the energy by a factor lambda will also cause the mass and momentum to also be multiplied by that same factor. But in trivial scale invariance, the mass is 0, so it doesn't really matter. So the momentum will scale the energy, and that's fine. That exists in particles like photons, which are massless. Unparticles are non-trivial scale invariant, meaning that they do have mass. So this is unlike any known particle, and that's why it's called unparticles. So this would be a key fundamental addition to the standard model, because it is something completely different than what we know. And this would be completely unlike a discovery of a new particle through supersymmetry, which would just add more known particles to the standard model.
So we talked about what an unparticle is, or at least what it should be, but how do we actually see unparticles in our experiment? Well, unparticle interactions have missing transverse energy from the standard model prediction that changes how the interaction is detected from how we would expect it to work. So there are 5 different diagrams that work. I'm going to talk about 3, and then Reed's going to talk about 2 in the next slide. But basically it's monojet, single photon, Z, diphoton, and dilepton diagrams. And all 5 of these diagrams produce unparticle stuff. It's not actually a particle, it's just stuff. So this unparticle stuff comes off of the diagram and basically manifests itself as missing energy from the products. And it also changes the output angle of the products of the interaction. So we can tell based on our detector simulations how it should be and how it is. And based on that difference, we can figure out whether unparticles are present in the interaction that we're detecting.
So the other 2 interactions with unparticles are unparticle-mediated diphoton and dilepton productions. Modeled here is basically, the diagrams both look basically the same. It's just over here would be swapped out for photons for diphoton. And normally this interaction can only be mediated by either a photon or a Z. But if unparticles exist, they would be able to mediate these interactions as well, which would create noticeable increases in just the number of events, at least in certain cases, of this interaction. And so if we detect an unusually high number of them, that would be evidence for unparticles. And for example, the diphoton interaction, it's predicted that there will be like a substantial increase in the number of interactions at very low rapidities. So basically, as close to the beam pipe as possible would be the best place to look for an increase in diphoton production due to unparticles. And then in the case of dileptons, it's predicted that if the unparticle coupling constant, or just like the kind of strength of the interaction with unparticles, is about 0.4, that would be the most likely scenario in which dileptons would be like noticeably higher in production due to unparticles.
The accelerator that we would use to find particles would be located at Illinois Mathematics and Science Academy in Aurora, because it could have the infrastructure that it needs to. The way the design works is that we have a 10-meter linac that feeds into a smaller ring, which goes into another ring, and then that ring goes through a linear pipe into a double beam pipe final ring that's much bigger. If you look at the bottom picture, the red boxes are RF cavities, and if you look at the picture on the top, that's to scale. The linear pipe is tangent to the final ring, and we use double beam pipes so that we can collide protons coming from opposite directions.
So just talking more about the RF cavities, another thing that we had to take into consideration was actual size. And so we decided to use one NeV RF cavities, besides the fact of it being cost efficient, also because when we did our luminosity calculations as well as our total collision energy calculations, we realized that the RF cavities were essentially negligible. And so as for our actual values, our total collision energy for two protons against each other would be 222.79 TeV, and then our luminosity value was 1.49 times 10 to the 41.
So based on the pricing information that we were given, we graphed these equations which represent the relationship between our possible maximum momentum if we spend all our leftover money on magnets and the magnetic field strength. And what that shows us is that our optimal magnetic field strength for our magnets around the beam pipe is 9 Tesla. When we did our synchrotron radiation calculation, we found that it was a little over 29 MeV. So that our accelerator would work, we had dual 15 MeV superconducting RF cavities on each beam pipe, so that we get just over that 29 figure.
So for central tracker design, for the first few cylinders, we use the silicon pixels because it's close to the beam pipe, so we want really good resolution. And then for the next cylinders, we use the double-sided silicon strips because it's further away, so it doesn't quite the resolution of pixels, but we still want the resolution. And then we did use like multi-layer chambers or stuff like that because it would cause the stuff or other stuff outside of it to be bigger and cost more money. The cylinder height's 1 meter to 4.5, and then there's 4 discs on both ends with silicon pixels, and then the total cost is $2.5 million.
So the solenoid we used had a magnetic field strength of 10 Tesla, and using this equation with L being the path length of the particle traveled, and S being the distance between two pixels, we were able to find that at 8 equals 0, the maximum transverse momentum was 10 TeV over C, and at 8 equals 2 was 14.77 TeV over C. And here we have this lovely rendered image of the tracker cylinder.
So up next we have our electromagnetic calorimeter, and it's made from entire layers of lead tungstate scintillator, with each layer being 25 millimeters thick. And each segment uses an avalanche photodiode detector. Now on the barrel we have 26 layers with a phi segmentation of 50 and an eta segmentation of 10. And the end caps have a phi segmentation of 24 and an eta segmentation of 6. It's 6.25 meters in length and 1.725 meters in radius, and has a final cost of $582.975 million.
To calculate the energy for the EM calorimeter,
we use the equation given here, which calculates the amount of energy given L radiation length. So it's the integral as shown there. And then within that equation, A represents, A equals 1/2 natural log of E divided by the critical energy plus or minus 1/2. And approximately 100% of the energy is absorbed by the light tungsten, since the given equation equals 1.0000 for electrons and photons at 223
TeV. So I did the clustering analysis for the electromagnetic calorimeter. So first, what I did was to find to find theta, which I did by getting the inverse or the arctan of the distance between the particle beam and the and the ecal divided by the distance between the interaction point and the ecal, so height divided by length. And after that, I plugged in theta into pseudo rapidity in order to calculate my my eta max and my eta min, which is basically, since our tracker is symmetrical, it would just be eta times 2, which is shown in my equation up there. And we did this to create, I did this to create a 2 pi eta space, which in order to find clustering analysis in jets, this is a little different than what's usually used, courtesy of equations courtesy of Dr. Dong. So what we did is here's our 2 pi eta space, and then our estimated radius per jet was 0.5, and here I just I did circle packing in my 2 pi eta space to calculate the amount of jets detected, which is 77.254, and then rounded down 77. And then here you can see my equations to calculate my the amount of electron clusters, which is 2 pi eta space divided by delta eta times delta phi, which is 89 electron clusters.
So for our hadronic calorimeter, we have 160 alternating layers. Each layer is 5 centimeters of thickness, and the entire unit is around 7.5 meters long, and it is 5.75 meters wide. It has the same eta and phi segmentation of the EM calorimeter of 10 and 50. And our goal when making this is cost efficiency. So we have polyvinyl toluene vacuum phototriodes and brass absorbers, and our final cost is $480 million.
For the energy analysis, we used similar equations to the electromagnetic calorimeter. Since our H-cal uses brass absorbers, the critical energy is 19 and 1/8 MeV. And by using this formula, we come to the conclusion that all the energy is positive, but that hadrons are absorbed when E equals this equation. This final answer is 137 times bigger than what it should be, because I made it over there. So it should be in the hundreds, not that.
It's down.
Up.
Page down.
Preston.
Up there we go.
You're right there.
Okay, so our muon detector consists of 1 iron return yoke, 4 toroids, and 10 layers of resistive plate chambers, or RPCs. So there's 2 layers of RPCs between the return yoke and the first toroid, and they're spaced 2/3 meters apart. And there's also 1 RPC between consecutive toroids with a spacing of 1 meter, and within each toroid spacing of 0.5 meter. So because our detector uses a magnetic field of 10 teslas, we decided to use a thickness of 1 meter for our return yoke, and we decided to use a spacing of 2 meters between consecutive toroids. So the final cost for a muon detector was $1.944 billion. And here we have a visualization from a side view of the muon detector.
Okay, so using some trigonometry along with the equation S equals QBL squared over 8PT, we were able to find the maximum transverse momenta that were measurable in our muon detector. And we found that for a track with eta equals 0, we got 1.13 TeV over C. And for eta equals 2, it was about 16.5 TeV over C.
Oh, and I guess that's the end. So, Dr. Dolan, do you have questions for the collaboration?
Sure, yeah, great job. I was really impressed by the think of everything, accelerator, detectors, plus not only the design, but kind of figuring out the maximum energy you figure out. That's a really good way to think about things. So I was wondering of those 5 Feynman diagrams you described at the beginning, is there one of those that you think would be best for discovering muon particles? For some reason, maybe the background could be different.
The cross sections are pretty different. I believe monojet is the highest cross section. I believe.
Which one?
Which one? What's the order of cross section?
You tell me. He's right. Monojet's highest. He's right.
Yeah, monojet is the highest, and then it's single photon D, and then diphoton electron D. So this is the most likely.
And then in terms of other things that could be happening in these collisions that would produce similar signals that would be like a background, have you considered at all if any of these would have fewer backgrounds?
Well, we did consider that the jets might be a little bit harder, especially with where detectors built, since we port a lot of them on the MCAL. So we were maybe trying to focus a little more on these two. Yeah, no, we didn't really consider that much of it.
Yeah, I think it's a good idea, right? You're colliding protons, so most of the things coming out are going to be quarks and gluons and things that make jets. So anytime you have a photon or a lepton, you can have a lot less background, so that's good. And I think maybe some of the 2 lepton ones could be really low backgrounds and could be a good choice too. Great. I was also wondering, so you made a proton-proton collider, but it seems like to produce these on particles we need a quark and an antiquark. So where are you going to get the antiquark from?
Oh, guys, you should know this.
I hear some good words behind
yeah,
the
C
quarks.
within protons, there will be all the C quarks and antiquarks.
Right.
For the sake of a collisions, basically, like metal work, that would create plenty of antiquarks.
Exactly, yeah. So the proton always has 2 up quarks, 1 down quark, but then it has all these other quarks that are popping in and out of existence, and some of those are antiquarks. So yeah, you could get an antiquark colliding with a quark when those collide. And so, like the Fermi Lab used to have a proton-antiproton collider, which would have been really good for this. But then something like CERN has a proton-proton collider, and you still get plenty of quark-antiquark collisions. So, yeah, good. What else did I have? Just out of curiosity, if you had a bigger budget, where do you think you would have put the money in order to improve your resolution? Would you have built stronger magnets? Would you have improved your segmentation or your detectors? Anything?
Probably increase the energy, just because the higher energy we get, the more the energy.
So energy scales was a cross section also, so you produce more of them. Okay. And you'd be searching in a region, basically you'd be looking at the rapidity distribution, is that correct? So something like the Higgs discovery was maybe a little bit easier because you could look at this mass distribution and you'd see a bump at a certain spot. Where here you wouldn't have that bump. But in the rapidity distribution you would maybe just see more in excess of events that are kind of at 0 rapidity. Good. Yeah, so there's a reason this kind of thing is a little bit harder search to do because you don't get that nice bump, and so it makes things a little harder. But I think it was a good plan. So, yeah, thank you.
I like her name. Yeah, it's wonderful.
Here, I'm going to explain a proposal for the Prometheus detecting precision Randall cylinder gravitons and Prometheus stands for property rights of mathematics and science in Illinois, entitled to everyone, entitled to honor everyone under science.
Okay, well, with that, I'll take credit.
First, to understand gravitons, we need to understand the hierarchy problem, which represents the difference between the two main energy scales, the electroweak scale and the Planck scale. And we are using the mass of the Higgs boson to understand this difference because the mass of the Higgs boson, which is 125 GeV, naturally falls in the Planck scale. But when we measure the mass, we find it to be closer to the electroweak scale, and there's that, you see the giant difference right here. And to get this difference, we use a method of fine-tuning to allow the mass to decrease from the Planck scale to the electroweak scale. But the problem, what the hierarchy problem is that when fine-tuning, we give extremely specific parameters for the decreases in the mass, and those parameters are very absurd and artificial. So we are actually doubting the accuracy of such methods, and that's why we're trying to find gravitons to allow us to get a more reasonable explanation for why this decrease is there.
So basically our proposal is inspired by the random sum model, which is a theoretical model that is supposed to provide a resolution to the hierarchy problem. In particular, the random sum model is based on several critical assumptions. One, of course, mainly being that there exists a 5-dimensional bulk, and that the boundaries of the 5-dimensional bulk is formed by 2 3-branes. One of the 3 branes is our observable universe, and the other is the Planck brane. The random sum model theorizes that gravitons will move freely through the 5-dimensional bulk, and as it moves freely through the 5-dimensional bulk, when it interacts with our 3-brane, it has become exponentially scaled.
Okay, so how does the model actually solve the hierarchy problem? As we already established, there is a Planck brane and there is a tau brane. Now the Planck brane has positive brane energy and the tau brane has negative brane energy. Therefore, they have opposing energies and this creates the warp factor. Now the warp factor is based on many things, including brane tension and such. But to make it simple, we're going to say that it's going to be 16 units. Now, this warp factor allows from something on the Planck brane as it travels towards the tau brane to exponentially change. Therefore, what we see on the Planck brane seems a lot, let's say, stronger than on the tau brane. And in this specific case, using 16 units, it would change 16 orders of magnitude, which gives us that boson, which gives us the boson from where it naturally falls to where we would like it to be.
So, is the model accurate? So, to be accurate, we obviously have to be able to detect gravitons, which is the main part of the random sum model. And since we're not able to directly detect gravitons, we instead have to detect the particles from the pair production of the graviton and find their invariance mass. And if we plot that, we get a graph like this, which is the x-axis is the invariant mass and the y-axis is the cross-section. And whenever we get closer and closer to the mass of a particle, we get these spikes, which are resonance peaks. And to find the graviton, we would have to get find the resonance peak of the graviton, and it'd be more accurate if we were able to find this resonance peak.
Okay, but how are we actually going to get the collisions that will form gravitons? Well, for this, we proposed an accelerator and in this design. So this is the most zoomed out diagram, and you can see that there's 4 rings. The 4th ring is about 41 kilometers, and the 3rd ring is about 2 kilometers. The 2nd ring is 140 meters, and the 1st ring is 5 meters in radius. And as you can see, we have LINACs. There are two LINACs because this is a proton-proton collider with double beam pipe. And there are 704 RF cavities per LINAC, and the length is 302 meters per LINAC. All of the rings have a 9 Tesla superconducting magnet. The fourth ring also has 31 RF cavities in order to combat synchrotron radiation, and all of the other rings have 1 RF cavity each. And the accelerator is constructed around a central meeting point in order to reduce the costs of travel pipes between all of these rings.
For the luminosity calculation, we use this formula: L is equal to F times N1 times N2 over 4 pi times sigma x times sigma y, where F is the collision frequency, N1 and N2 are each the number of particles per bunch, and sigma x and sigma y are the beam widths in a given direction, x or y. And so for our numbers, F is equal to 25 inverseconds using the length of the bunches and the distance between the bunches, and also the fact that they're traveling at the speed of light. Then N1 and N2 each were 1 times 10 to the 12 particles, and sigma x and sigma y were each 2 times 10 to the negative 5th meters, giving us a luminosity of 4.97349 times 10 to the 33rd, 1 over meter squared seconds.
Now, in order to calculate the cost, one thing that plays in as a major factor is the fact that we have to build our accelerator approximately 100 meters underground. This allows additional radiation shielding and provides additional safety benefits to the workers. But it does mean that about 50% of our total costs come from the tunneling costs. For our linear accelerators, each one costs about 24.74 million United States dollars, but because there are 2 of them, that cost is doubled. Starting with our innermost ring, that costs 3.574 million US dollars. And for each ring after that, each ring is 20 times larger in circumference, so the cost multiplies approximately 20-fold. That means our second ring is approximately 71.074 million US dollars, our third ring is 1.4 billion US dollars, our fourth ring is 28.421 million US dollars, for a total cost of 29.89 billion US dollars.
Okay, so our tracking detector was designed using carbon nanotubes and silicon pixels to make sure that it was going to be very small while being very accurate, as we found that carbon nanotubes could be treated to make them into semiconductors to be able to be used in a detector. So it ended up being only 0.165 meters in radius and 3 meters in length to capture as many particles as we can. And then the carbon nanotubes have a maximum of 10 to the 8th wires per meter, which compares to the single-side silicon pieces, which are most easily compared to it, which only can have about 12,000 wires per, say, meter. These carbon nanotubes also require half of the gap for cooling as silicon does, as well as being 5 magnitudes thinner than silicon. It also, we optimized the design of it by designing it angularly segmented so that we have much more accurate materials towards the center and less accurate materials towards the end to save prices while also getting the best data we can. Our design ended up having 6 layers near the end and 9 layers in the middle where the carbon nanotubes are, and 5 layers of end caps. And we can capture over 98.3% of all particles that go through 1 or more layers. The total cost ending up being 2.6 billion US dollars.
So we wanted to also determine exactly how sensitive this tracking detector was. And so using the calculations above, we were able to find that when eta equals 0, our tracking detector can detect a maximum transverse momentum of 1,876.677 tera-electron volts. And when eta is 2, its max transverse momentum is 9,004.28 tera-electron volts. And the reason that we're able to reach such an incredibly high transverse momentum detection is because of our nanotube semiconductors, which are incredibly precise, backed up by our silicon pixels, as well as our segmented design, which allowed us to use these incredibly costly devices while favoring for efficiency in our most efficient sections of the actual tracking detector.
for a vertex analysis, because our inner layer of our tracker is made of carbon nanotubes. For physical reasons, the minimum space, this is between, this would be 5 times 10 to the negative 8 meters. And so that means the smallest interaction points of two different tracks of particles would be about 5 times 10 to the negative 8 meters. And so when you take a look, like as you see in the graph, when you compare the two tracks of particles from the two different vertices, you get that the distance of the two vertices is about 9 times 10 to the negative 8 meters.
The next layer in our overall detector design is the electromagnetic calorimeter, and we opted for a sampling calorimeter design. It features 44 total layers alternating between lead tungstate scintillators and depleted uranium absorbers. And we chose these because of their extremely low radiation links. With these, we use vacuum phototriodes as the detectors for the particle energy, and every layer we had with decreasing thickness, with the thickest layers being closest to the beam pipe and the thinnest furthest. And you can see the starting and ending on the screen. We did this for cost efficiency because this vastly reduced the amount of vacuum phototriodes we would need, and each one costed a significant amount more. But doing this, we were still able to ensure that our calorimeter could measure particles of up to energies of 10 times. The end caps we have exactly identical in quantity and material, and then every particle ends up going through at least 31.32 total radiations. With this efficiency, we still were able to reduce our costs down to $122.356 million US dollars.
To calculate the maximum measurable energy for our eCal, we first set a final cutoff energy of 1 GeV. This ensures that we measure over 99.99% of all particles' energy. Afterwards, we use the equation shown above to find the amount of energy lost per radiation link and solve recursively for all 44 layers of the main eCal as well as through the end caps. Afterwards, we adjusted the initial energy until we reached the cutoff energy to find our maximum energies. We found that when the particles escape perpendicularly to the beam pipe at eta equals 0, we can measure a maximum energy of about 10.2 TeV. Meanwhile, if they escape at an angle of about eta equals 1.943, which is the minimum eta at which they can go through all of the end caps, we can measure energies up to 25.9 TeV. And the reason why there is such a great difference between going through the end caps and going through the main body is because when the particles go through the end caps at an angle, they interact with more of the material, which allows greater reduction in energy.
So for our clustering analysis, we wanted to find an estimation of the distinct numbers of energy clusters that we would be able to find with our calorimeter. To do this, we used the maximum angle for which all the particles would be passing through the end caps to set our maximum and minimum eta for eta phi space. We then converted the Moliere radius for our absorber material into an angle to be the radius of the electrons in eta phi space, using a radius of 0.5 for the jets. At that point, we just solved the packing problem to find how many circles of that radius could fit in our space, and ended up with approximately 95,000 measurable distinct electrons and 21 measurable distinct jets.
So for the hadronic calorimeter, we have a basic design of alternating layers of plastic scintillator and mercury. Mercury having an interaction length of 14.85 centimeters. There is a total of 24 layers of the mercury, and the end caps have only 4 radiation lengths. Don't panic though, because the barrel of the hadronic calorimeter goes out and stretches out to where the eta value of everything that passes through that is 7. So at this point, we don't even have to really worry about end caps, but they're there just to catch anything that goes like straight down the beam pipe. This total thing is total cost of $3.848 billion US dollars.
So using a spreadsheet with various calculations and everything, we determined the various energy values for each of the particles coming through the hadronic calorimeter. So for the barrel, the particles enter with an energy of 10 TeV, and as energy is absorbed, the particle will exit with an energy of around 0.7 TeV, meaning that 9.35 TeV was absorbed. And for the end caps, the particles enter with an energy of 0.65 TeV and exit with 0.62 TeV, meaning the total energy absorbed by the end caps was 0.03 TeV. Together, the HCal absorbs 9.38 TeV from the particles, or 94.7% of the particle's energy.
What button was it?
The down arrow.
The focus of our muon detector is to help aid all the other tracking systems within our collider. To help with this, our muon detector can specifically help by measuring low energy muons and help find and identify paths from the immense precision of our central tracker and identify them specifically as muons because only muons will be present within our muon detector. On top of that, taking cost into consideration, we wanted to allocate some budget towards the other parts of our detector, and on top of that, we made sure to include the bare minimum to allow us to identify the tracks from the central tracker. This included us having end caps and our central muon tracker to have both return yokes that were working and also enough layers to enable good measurements of muon PT and beam pipe splash from muons. As for the goal of deciding which paths are muon paths and for which particle to make sure not to mix them up, we opted to use clustered spacing as it will allow us to differentiate the different paths once they get close to each other and provide accurate extrapolation of where the particle's path will be based on the equations that we have for momentum.
Alright, so to calculate the maximum transverse momentum, we use the equation as shown, where S is the saturator value, which is the distance between the particle's trajectory and the core connecting the starting point and that ending point. And V is the strength of the magnetic field in Tesla. L is the path length of the particle in meters, and the transverse momentum. PT is the transverse momentum. And through some geometry, given a core length of 0.9 meters, the saturator value of 1/100 meters, the length of the particle's trajectory is roughly the value of the core connecting the particle's starting point and ending point. So at eta equals 0, the maximum transverse momentum is around 40 GeV, and at eta equals 2 is roughly 2,129 GeV.
Dr. Dolan, good job. Once again, yeah, we went over everything, so that's really good. Okay, really cool. First question, why 2 linear accelerators?
Oh, because each one is gonna like accelerate the protons.
So you have protons going one way around the one with the ring,
Yeah.
the other way around the ring.
It's double beam type.
Double beam. Okay, cool. And then for the Randall syndrome graviton, you said you can't directly observe that. So what are you actually observing when you try to detect that graviton?
We're observing the particles that are formed after the pair production of the graviton.
So the graviton is going to decay into
Yeah.
something. Do you know what those particles are potentially, or?
Not really. It's gonna be detectable known particles though.
Yeah. So I think it will decay into some standard model particles that we know, and perhaps 2 quarks.
It's like the interaction will be similar to Drell-Yan, so or like other interactions, like there'll be a particle and an antiparticle, so like a quark or an antiquark or a lepton or an anti-lepton.
Okay. And then you can hopefully measure both of those particles and then maybe plot their mass.
Yeah.
You see a bump at like the Randall syndrome graviton mass. Okay, good. So yeah, you built a really nice kind of multi-purpose detector that could detect pretty much any type of particle because you have all these different layers. I think the reason I'm asking is, if you were to build a detector that only had one goal to just detect one particle, in some cases you could just make it cheaper just by figuring out what are those particles that you're expecting to see and forget about everything else. Like if you were that graviton was decaying to muons, you could almost build a big iron ball and then put a bunch of muon detectors on the outside of it and you could find it. But I'm glad you built a multi-purpose detector so you can see everything. So, okay. I was curious about how did you decide how many protons were in per bunch in the accelerator, which determines the luminosity? Is that the luminosity calculation?
It was just a term. It was like a standard set by.
Oh,
I made up a number.
Okay. Yeah. And you could compare it to Fermilab or CERN, and obviously, yeah, the more protons you could get in per bunch, kind of the more collisions per second you'd have. But of course, they're also protons, so they're repelling each other. So, you know, at some point you can kind of lose control of them if you try to put too many in there. Okay, and then who was the next question? And then what advantage is there to have really good vertexing? As you guys, with the nanotubes, you claim that you could have a really good vertex measurement. What does that bring you? What does that provide for you?
Means that like we can distinguish as many particles as possible. So like we have very precise measurements. So we're like able to increase our detection rate and our efficiency.
And especially near the center is where all of them are clustered. So it's more vital to make sure we get as precise as possible.
Okay, yeah, so you could see where all those particles are originating from and see them all coming out right away. You try to get your detector kind of as close to that point as you can. Okay. And then, yeah, you'll probably have more than one collision happening at a time, actually, right? So that could be really good to be able to separate those different collisions. And maybe one of those collisions could be like the really important collision that is producing your KK graviton or your RS graviton. And the other ones could be kind of junk, so yeah, the resolution could be really helpful. Great. Okay, last question, why Mercury? That's neat. Yeah.
The original idea was to mix the mercury with something like a uranium to create a mercury-uranium amalgam, but we never actually got around to sending that information off to our Dr. Dom. So, thanks for that.
You're welcome.
But anyway, so we just settled on the mercury, partially because whenever you looked at it with the interaction lengths between like the light tungstate and all those that you had, the mercury seemed to have a much smaller interaction. So whenever it goes into putting everything outside, we were able to fit more of it into a tighter area. As well as the engineering wise, it's kind of easier to have a liquid there that you can set something in there rather than having to cut metal.
Yeah. Yeah, maybe with cooling you could move the mercury around a little. Yeah, I'm worried about mixing mercury and uranium could be the most dangerous substance ever created.
Just a little bit.
Okay.
All right. Well, Dr. Dolan, if you were a funding agency and you had only the $38 billion necessary to fund one of these two collaborations, would it be the unparticle detector or the Randall-Sundrum graviton detector?
Well, that's a tough choice. I think I'd encourage some collaboration, and maybe you can build a detector. But I think I'm going to vote for the unparticle detector. I thought it was a little bit more complete, and I really like that you went through all the different possible signals that you could find, and so you know which detectors could be seeing which signals. Part of the planning process. But yeah, every group did awesome. So yeah, good job.
Thank you. So I think we are. Did anyone have any questions while you have a collider physicist in the room? For the record, Xander, I think that the gravitons can go to either leptons or to jets, so you could do a dijet or a dilepton analysis.
Yeah.
All right. Well, thanks again to Dr. Dolan, and we'll move on to the next part of our.
Yeah, nice to meet everybody. I'll be around if anybody has any questions.
All right. Thank you.